Hello students, in today's class we will read electric field lines and we will define these field lines. We will understand how we are able to take an idea of what kind of charge is placed in the space using these field lines. Once we will understand about these field lines, we will know the importance of these field lines too. So, starting up the class, field line is a vector quantity and it's represented as a vector. As we have seen, in the field line formula, we always apply an arrow at the head of our capital E, and capital E denotes the electric field. Electric field. Now let us try to represent E due to a point charge placed at origin. Our point charge is placed at the origin. This is our origin and we have placed a point charge over here. So how this charge which is placed at the origin, how is it working and how it is producing the lines, how these lines are helpful in nature, we will see this. So drawing vectors pointing along the direction of the electric field with their lengths proportional to the strength of field at each point. What we are doing, we are drawing the vectors which are pointing to the direction of electric fields, and whatever length we have taken will show the strength of that field at that point. See the diagram over here. This is the point charge and these are the length. If we suppose that this length is 2 cm, then this will reduce to 1.5 as the strength is reducing, and again this will reduce to 1 and so on. This will be 0.5 and again it will be 0.25, maybe lesser than that. So as we move away from our charge, these electric fields and their strength will start decreasing. I'll write over here, strength decreases away from charge. Away from charge. Since the magnitude of electric field at a point decreases inversely as the square of the distance of that point from the charge, the vectors get shorter as one goes away from the origin, always pointing radially outward. This is a defining property of our electric field. It is radial in nature, and as the charge is positive in nature, what is happening? They are going outwards. In the next slide, we will see the electric field lines properties when our point charge is positive in nature and when our point charge is negative in nature. At the origin, we are having a positive point charge. Hence, what is it? What we are getting is our radially outward from the origin. We are getting these lines as radially outward. Now the strength is defined as, it is shown by the length of arrow. Whatever is the length of the arrow, that will show us the strength, whereas the magnitude will show us density of field lines. What is the magnitude of the charge? And as we go away from the charge, it reduces, so the density of the charges also reduces in our given space. So I will explain these 4 points along with the last point in a diagram. Let's read out the last one. E is strong near the charge, so the density of field lines is more nearer to the charge, lines are closer. Away from the charges, the field lines get weaker and the density of field lines is less, resulting in well separated lines. So what all these things are saying, we got a point charge which is placed on the origin. Away from the origin in all the direction, that is radially outward direction, up, down, right, left, this side, that side, in all the direction. How, just assume a spherical charge. Okay, just assume our charge got a shape of sphere. A sphere is a three-dimensional circular object. So from all the direction, this electric field lines are coming out. So if we see here at this point, in this much area, we will find that electric field lines are closer to each other. That implies they have higher density near the charge and hence have more strength near the charge. Okay, high density near the charge. So they have more strength over here, and even the length of this arrow is bigger. Now if we go for the second circle, this is smaller length, this is smaller length, and see the distance, how far these two lines are. So here the density is decreasing and hence the strength decreasing, and here of this arrow magnitude, this arrow's length is less when compared to this arrow, and hence we can conclude that now the magnitude of electric field is reducing. Magnitude of E is reducing. So that is how, if in a picture form they have given us the electric fields, we have to define. Nearer it is more, and as we go far it is less. The magnitude as well as the strength of E are decreasing as we go far from the charge. But another concept over here is these number of lines are not important. For this given charge, we can make n number of lines. But line per unit area is important. When we are near to this, we have taken this area. How many lines are passing through? If we say n lines are passing through, same area, this area is taken at r distance. At r plus r distance, we have taken the same area, and now how many lines are passing through it? N minus 10 lines are passing through this area. So the relative number of line passing through the given area defines the strength of the electric charge at that point, not the number of lines. We can draw infinite. In fact, an infinite number of lines can be drawn in any region. It is the relative density of the line in the different region which is important. Relative density, relative to point A, relative to point B, or relative to origin. On the plane of paper, two-dimensional lines are drawn. Here see, I can draw up, down, left and right, but I cannot draw inside and outside, right? On the paper, we have our limitation up to 2D diagrams. We cannot go for the 3D. But we draw lines in 3D. So to estimate the density of field lines, one has to consider number of lines per unit cross-sectional area. Per unit cross-sectional area perpendicular to the lines. Line per unit cross-sectional area, and that area should be perpendicular to the lines. Just take one example, okay? Do one activity alone with me in the class. Keep your hand in a same direction. Like you are asking your mother to give you some money. Okay, in that position keep your hand. Keep another hand in the same position that you are asking your mother for the money, and take both your hands at 90 degree. See, I'll draw over here. Okay, so this is how our hand is, and another hand we have taken like this. Okay, so these both hands are, this is electric field, this is our area vector, but these electric fields will go from here but never go through this hand. But in the other situation, keeping our one hand like this and the other hand in this way, in a standing way, like you are stopping someone. Okay, your hand is coming from this direction, and you with your right hand you are stopping the left hand to go further. So what happened in this case, these electric field lines will move from here to here. So this is called that our area element is perpendicular to the electric field lines. This is coming from here, going out, coming here, going out. So this, they both are making 90 degree of angle. But here another concept which we need to learn is the vector associated with this area element is along the direction of electric field. Vector associated with S, that is area element. S denotes area. Area element is along E. Okay. Since the electric field decreases as the square of the distance from the point charge, and the area enclosing the charge increases as the square of the distance, the number of field lines crossing the enclosing area remains constant, whatever may be the distance from the area of charge. See here the pictorial representation. We are having a charge here, Q, point charge over here, and this one is a one area R, and this one is another area S. Here, as the distance is increasing, the area is also increasing. This is circular in nature. R is circular in nature. R equals to circular. How do we find the area of a circle? It is pi r square. Here, from here, if we will find the radius of it, it will be some r. So it will come pi r1 square. We will take area of radius of this as r1. Now at S, this is also circular in nature, and similarly we can define area for that also, and it will be pi r2 2 square, as r1 is at a distance of r and r2 is at a distance of r plus some other value, maybe some y, so farther, and these are dependent upon the inverse square law. These areas are also increasing. From R to S, area is increasing. So what happens, that number of field lines which are passing through R are exactly same the number of line passing through the S. I will give one more example for you to understand it nicely. In a square, like we will take a square, case of square area, so that we will find out this one, area at distance r1, area at distance r2, and we will correlate it to understand what is inverse square law and how it is being applied, and why we say that at two different places area also is increasing, and hence our relation is coming in this way as the point number 3 in this slide is suggesting us. Now see, this is a point. From here we have to calculate the inverse square law. We have to understand what is it. So at this particular distance, this is the area. At this particular distance, if we will find out properly, this is the area. And now at some other distance also we will find okay. So this is the area at distance 3. Now we will go with numeral values now, so that it should be very much clear to us how we are trying to predict, how we are trying to make it happen. So over here we'll take it as 1 meter of distance from this point. Here we will take 2 meter of distance, and here we will take 3 meter of distance. Now we have taken the distances from here to here. What is the area of this part? It is 1 meter square. 1 into 1. What is the area of this? 1 unit for this, 1 unit for this, 1 for this, 1 for this. This is 4 meter square. Similarly, what is the area of this? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is 9 meter square. So see how the relation is there with respect to distance of area. From 1 meter away from the point charge, area is 1 meter square. For 2 meter away from the point charge, area is 4 meter square, and similarly for 3 meter it is 9 meter square. So area is also increasing as a factor of square to the distance. Area is showing a relation to the square of distance, square of distance. This is exactly what our third point aim at saying. As the distance increases, area also increases. So the number of field lines passing through this area also remains same. From this, as this is near, this area is near to the charge, many field lines will pass through. But as we go here, there will be some reduction because the field lines are moving apart. As the distance is increasing, field lines are moving apart. As further distance is increased, field lines moved more apart. So for this, there will be lesser number of electric field lines. So when we aim at comparing the number of field lines for 1 meter square, 4 meter square and 9 meter square, it is same. It is same, constant. It is not like that the area increasing implies number of field lines passing through it also increases. No. Okay. Hope the statement is clear. The field lines crowd where the field line is strong and are spaced apart where it is weak. Wherever you see the crowd of field lines, we can conclude the field lines are stronger here. See, I'll give you one example. We are having a charge over here and these are the field lines coming out of it. Okay. Now I have placed a point over here, a point over here and a point over here. This is point A, this is point B. Now tell me which point will experience more force from this charge. A will experience more because the number of field lines which A is able to get through it are more than the point B. A will experience more force than B. It is a very much important and a favorite question for board examination as well as many other your entrance examination. So this should be paid attention. This is a direct question. They will give you a similar diagram with similar A, B and C point, and they will ask you which point is experiencing weaker force and which point is experiencing more force or the stronger force comparing to this, or write point A, B and C with respect to the force they are experiencing in decreasing or increasing order. This is a direct question. So if you understand this question, this will make you get a very good score whenever such questions are appearing in your examination. Now we can imagine two equal and small element of area placed at point R and at S normal to the field lines there. Here to the field line R and S is placed. Now field lines are proportional to the magnitude of field at these points. The picture shows that field at R is stronger than field at S. As I explained, this is R, this is S, and from this diagram also one can conclude where the field line forces will be more. At point R it will be more and lesser will be at point S. To understand the dependence of field line on the area, how they are dependent upon the area or whether on the solid angle subtended by the area element, let's try to relate the area with the solid angle. A generalization of angles to the three dimensionals. See, X, Y and Z. There are three dimensions. In this three dimension I am having a sphere with its center at origin. Now you have to visualize it. I cannot draw it in a plane of paper, but you have to visualize like an angle, a conical angle coming out of here, a conical angle. This is cone shape, okay? Something like in 2D what we make. For this circle we will make a triangle to show the angle, but the same triangle with a circular end, circular top, which forms a cone like structure will give us a solid angle, okay? Solid angle is a generalized angle for three dimension. Now let a small transverse element, line element del L be placed at a distance R from the point O. So I'll draw a better diagram over here so that we can clarify each and every point. So this is our angle in the sphere. This is our sphere, I am making it roughly. This is our sphere, this is the angle subtended, and this is del theta. This is del theta. Then the angle subtended by del L at O can be approximated as this. At this particular line element, this is a line element at some point X. From that we are subtending this particular angle. R is the radius of this spherical body, or R is the radius here, it will give this particular radius, and here will be the line angle. This one is our line. From this line we have made one angle, that is our solid angle in three dimension. That solid angle is defined as del theta equals to del L, the small line element which we have taken, divided by the R, the radius. Now in 3D, the solid angle subtended by a small perpendicular plane area del S. This is, we have taken this as line element. Now the other concept we are taking is this whole area, this whole conical ka circular area we are taking, okay, and at a same distance r, and it can be written as this is our three-dimensional angle del omega. Del omega equals to area upon r square, because here we will be working with two r, one from one dimension and the other from the other dimension. For the two dimension we take only one r, but when we are going for the three dimension, there will be the distance which will be having correlation with either or the axes like x, y or z axis. So it's very much compulsory when we are taking account of an area, it should be like divided by r square. So just memorize this one. For a solid angle in 3D, our del omega is given by del s upon r square. It is a relation proportional to the r square. We know that in a given solid angle, the number of radial field lines are same. We have read in the previous slide already. At any distance for a given area, the area away from the charge increases, but the number of field lines remain constant. In the figure, 2 points P1 and P2 at a distance R1 and R2 from the charges in the element area subtending a solid angle of del omega is R1 del omega. This is the definition of our surface area. At R1 the surface area is given by this. This is the surface area for R. In the previous diagram, in the previous slide, for the diagram, this one is the R. Similarly, for the element area S, that is R2 away, like at a distance of R2 from the origin, it is away by the R2 distance, that multiplied by the angle. How is it coming? See over here, what we have defined omega equals to del s upon r square. Now we want to find the area at r, which is at a r1 distance away from origin. So it will be given r1 square into del omega. Similarly, area at S is R2 units away from the origin, will give R2 square into del omega. Okay, that's how we are finding the area at R1 distance and R2 distance. Number of lines, say n, cutting these area elements are same, though they are away, but as we have defined, it will remain same. The number of field lines cutting unit area element is therefore n divided by this, the number of lines n divided by their area, del s. Okay, at P1, for P1 we have taken R1 and at P2 it is taken R2 respectively. Since n and del omega are common, see in this n1 and these values are same for any distance. For any given distance, value of n for any given distance, value of n and del omega are same. This is a point to be star marked or highlighted. So what we aim to say by this is that strength of the field clearly has 1 by r square dependence. It depends only and only upon the inverse relation to the square of distance away from the charge or near to the charge. Now, the picture field lines developed by Faraday is a non-mathematical way to visualize electric fields around the charged configuration. We are not using the numbers 1, 2, 3, 4. We are not using the other alphabetical formulas like A plus B or sigma of A to B or something like that. We are just giving a pictorial form, and understanding a concept by the pictures is also very much important as well as easy. And once you understand, once you start visualizing something, it's very much it gets very much clear. So this pictorial formula was developed by Faraday, and it's a non-mathematical way of visualizing the fields. Now the Faraday, who have given us these fields, called it as line of forces, but these line of forces were misleading in the case of magnetic field. How does these line of forces mislead us? Was like, see, magnetic, we will be reading in our 4th and 5th chapter though, but still I'll give you one idea. Magnetic poles do not exist as monopoles. They do not exist as this, though our charges exist as single charges. Electric charges exist single. Secondly, these line of forces are the lines which defines the forces, but these anything kept in the magnetic field do not help us to find the force. Here in case of magnetic fields, magnetic field line, they do not give us force exerted. They do not give us force exerted, hence they cannot be called line of forces. Anything which is not giving us the example or numeral value of force cannot be said as a line of forces, and magnetic field lines do not give us anything related to the force. More appropriate term is field lines. So we say as electric fields and magnetic fields. An electric field line in general is a curve drawn in such a way that the tangent to it at each point is in direction of the net field at that point. These are curves. These are not straight lines as we have predefined it. These straight lines which we are defining are the tangents to these curved electric fields. An arrow on the curve is obviously necessary to specify dimension, direction of the electric field from the two possible directions indicated by a target to curve. So there are two possible directions for this tangent. For this curve, the tangent can go this way, and from this it can go this way, and this way also possible. So how far these are and in which direction they are moving, all these things, when we draw a tangent on this curve, specifies it. These targets specify to the curve. So these basically we draw and we define electric field in this way, not in like this. So this is our charge. In 3D it will be the electric fields, right? Not this way. This is a 2D representation. The 2D representation comes like this. The tangent from this, anywhere direction of the tangent will keep on changing. Like here it will be like this, here it will be like this, here it will be like this. What is a tangent? Do you know that one? Tangents are the straight line drawn to any curved surface, and they meet that curved surface only once at a single point. They do not have a bulk relation with the curved surface. I will give one example. See, this is our curved surface, and if this is a point, we have taken any straight line which is passing through this and only meeting at this point is called tangent to this curve. Tangent to this point, because at every point tangent is different. If you see a tangent over here, see, we can draw it like this. It is meeting here. For this point, this is the tangent. For this point, this is the tangent. So tangent gives direction at a given point in the electric field. A field line is a space curve in the 3 dimension. The field lines of a single positive charge are radially outward, while those for a single negative charges are radially inward. So see over here, this is a positive charge. Q is greater than 0. These lines are moving out to the Q. These lines are moving out to the Q. This is Q smaller than 0, that is negative. And these lines are moving inside the charge, inside the negative charge. For positive charge, radially outwards. For negative charge, radially inwards. Now we got two positive charges together. See, this is positive charge, this is positive charge. They will repel at a particular distance, at a distance where these field lines will start like overlapping each other. They will start repelling each other. Positive repels, or the like charges repel and unlike charges attract. So in this case, these field lines, due to these field lines there will be repulsion, and these field lines are going for both the charges. Though both the charges are into a same system, still these are moving like outwards. So anywhere, in any case, the field lines will move outwards. See, I'll show you the example for the negative charge. We are having this negative charge and this negative charge. How the field lines will work here? The field lines will come to this point. This will be the arrow mark over here. And similar way to this, it will come to this point. See, came. Okay, so similar way, in the same way, but here these are moving outwards, and in this case it will move inwards. Now this one, this is an example of electric dipole. Electric dipole. We have a positive charge here and a negative charge here. These electric field lines move outward from the positive charge and inward to the negative charge. Out, in. And for a given dipole, they constitute a loop kind of structure. But when we are dealing with a single charge, we will see that they will never form loops. There will be no closed loops. As we have already seen over here, electric field lines and magnetic field lines have these kind of small differences. They exist singly. Charges exist singly, and hence they do not prefer to form loops. How can they form loops? This is a positive charge. The lines are moving outwards. They cannot come inside the same charge. They need some negative charge to go, these lines to go inside it. That means they are not forming any sort of loops. Field lines around the two positive charges and a dipole is shown in this figure, as I have already explained. The field lines follow some important general properties. These properties are very much important on the basis of the board examination. As well as your entrances. They form concept based question as well as assertion and reasons. Assertion and reasons. So when we say the physics is all about the formulas and numericals, it is not so. Physics is also a theoretical subject. The theory in the physics is very much important to make any formula. Formulas we can derive by understanding, but theory we cannot, unless until we are not reading, we are not imagining the concepts here. Like most of the cases, the world is three-dimensional. We have to understand these concepts on the basis of three dimension. Then the world is macroscopic and microscopic. These charges are very small. They form a more good environment in the microscopic world, whereas in the macroscopic they have their different properties. See, in our general day-to-day life, we cannot see charges, but when we aim at studying a microscopic environment, we can see these charges as distinct population. See, I can just give you example of the world. Go far from the world, go into the space, you will find earth a small thing and you will not be able to see any humans from the far away. But when you enter inside the earth, you can see all these humans, animals and other small creatures. In a similar way, these charges are contained in a microscopic world which we cannot see, but once we enter into that microscopic world through microscopes or any other magnifying apparatus or instrument, we will find many small discrete things which need to be understood. So at this particular point we need to have a good imagination. So for that, these kind of properties which are present at the end of every topic, they have given us significance of dipoles, significance of field lines, general properties, this and that should be read very carefully and should be understood very clearly. So let's move to the point 1. Field lines of a single charge starts from the positive charge and ends at a negative charge. If there is a single charge, they may start and at an infinity. This is our single charge, positive charge. These lines have started. Where will they end? There is no negative charge, like there is no negative charge in the vicinity. They will end at infinity. Okay. Similarly, a negative charge is getting field lines from somewhere, but there is no positive charge. From where does this negative charge is getting these field lines? It is also getting from infinity. In a charge-free region where there is no charge, electric field lines can be taken to be continuous curves without any breaks. They do not break. Like this is a charge-free environment. Here we have a charge, here we have a charge. So there will be electric field lines. It will not be empty. They will be going from here to here, right? So these forms a continuous, no break lines. They are continuous in nature. Even though there is a system like this, here also they will be forming continuous. Always electric and magnetic fields in any scenario are continuous in nature. Continuous in nature. Two field lines never cross each other. If they did, fields at the point of interaction will not have unique direction and it looks absurd. How does it happen? Like this is our charge and this is electric field around the charged particle. Now the direction of the electric field is taken by a tangent. This tangent is moving from here and we have seen at this point the tangent is moving like this. So, and the same point a tangent is coming from here and this is moving in this direction. From this point we are having tangent 1 and tangent 2 which are giving us two different directions at some particular angle. How can this be a possible? Is this having a multiple kind of spaced region? So it is not present at two different points, it is present at a single point in the space. So it should give us a single direction. So this makes the situation very much absurd. It's not called a complicated situation or a situation to be learned. This is not possible at all. From a single point we will get a single direction, that's all. That's the definition of tangent. For every particular point, tangents are unique. No tangents are same. Like for this point we have a tangent over here, for this point the tangent may be like this. So tangents are unique, it should not be same. For one point it is only one, there will not be two tangents for a single point. Now fourth, electrostatic field lines do not form any closed loops. They follow from the conservative nature of electric field line. This concept of no closed loop formation satisfy the conservation nature of electric field. Conservative nature of electric field lines. Okay. So these are the important general properties of the field lines which one should read, understand, and the importance I will just recount it. From a positive charge, a field line starts, ends at negative charge. If there is just a single charge present, they may start or end at infinity. In case of a free region, these electric field lines are continuous curves and there is no breaks in these field lines, and the field lines never cross each other. That kind of condition is not possible. Each and every field line have a unique direction, and these electrostatic field lines does not form any sort of closed loop and hence follow the conservative nature of electric fields. So that's all for the today's class. We'll meet with the next and the other one interesting topic from the same chapter in the next class. Have a good day. Bye bye.